Okay, for our final video on the pigeonhole principle, really driving this one home because it is so useful. I've got an example that's a little more algebraic. So it's something that you might come across in 410 actually, or in number theory. So if you're taking abstract algebra or number theory, then one of these sorts of problems might come up at some point. Here's the problem. Pick any 6 numbers between 1 and 10. Now when I say numbers, unless otherwise specified, I mean positive integers. So pick any 6 numbers from 1 to 10. Then there are at least 2 such that one divides the other. We want to think about this, again, in terms of balls and boxes, in terms of the pigeonhole principle. Why? How do I know when I read this, other than the fact that it's written on the same page, that it's a pigeonhole problem? There are 2 such that. There are 2. There are at least 2. Whenever you see an indication like that, there are at least blank such that. That is an indication that you're probably in pigeonhole territory. Okay? So now you want to think, all right, well, here we go. At least one box that has at least 2 balls. There's my 2. Okay, so there are at least 2. Those are my balls. So there are at least 2. What are the balls? They're numbers. Here are my balls. These are the balls. So I'm going to pick 6 balls. And I want to make sure the pigeonhole principle applies. So how many boxes do I get? Well, my boxes are right here. N has to be less than K. So I want to have at most 5 boxes. Usually the way these problems are set up, you're going to have exactly the right number of boxes and the problem will work out nicely, but you never know. In real life, it might not be so nice. So that's what I'm going to want. And the boxes have to satisfy this property. Here's the property that we want the boxes to satisfy. So in the same box means one divides the other. So in each box, any pair of numbers, one must divide the other. Okay, that's kind of a crazy condition. But that's okay. We can handle that. So first of all, let's get some numbers. Here are numbers. Let's put them in some sensible order. How about numeric order? 1, 2, 3, 4, 5. Maybe that's the 6, 7, 8, 9, 10. Okay, here are my numbers. I need to group them together in a sensible way so that in each group, in each box, I have every pair of numbers, one divides the other. Okay, so 1 could kind of go in any box. I could think about prime numbers. Right? That's one way to divide this out because I could think about prime numbers. Whenever you're talking about division, well, 7 becomes a problem, right? Doesn't play nicely with many other numbers. But that's not really going to scale very well, and that's going to be a little tricky. And I don't know that I'm going to get the right number of boxes. So instead of picking out like 2, 3, 5, 7, and 9, I could do something a little different, which is I could say, well, I know I have 10 numbers total. I want to get about half into boxes. That could tell me maybe pick the odd numbers to go with. And that's reasonable. So let's think about that. Let's think about each odd number as sort of being in a box. So I'm going to put 1 in a box, 3 in a box, 5, 7, and 9. And these are all going to go in different boxes, okay? I've still got my other numbers to place in boxes, but these guys are going to be each in a different box, okay? Even though 1 divides 3 and 5 and 7, I mean, the 1 really can go anywhere. But okay, let's keep going with this. So 1, well, I'm just going to take a greedy approach. 1 divides 2, 2 divides 4, and also 1 divides 4. So the transitivity here is really going to help us. 2 divides 4, so as long as I put something that 4 divides next, any of these guys will divide it, so I'm going to take the 8. That is a huge box, but I don't care. I could have a giant box and all the rest small, and the pigeonhole principle will still apply. It'll just, in this case, I'll definitely have to pick a lot of numbers from this box. That's fine. Okay, 3. What does 3 divide? Well, 3 divides 6. Okay, 5. 5 divides 10. Well, the 6 didn't divide the 10, so I had to put it here. So these are my boxes. Have I succeeded? Have I successfully solved this problem? Let's think about it. If I pick 6 of these numbers, then I have to pick 2 from the same box, okay? So I'm not picking 2 from this box. It only has 1. If I pick the 5 and the 10, check. If I pick the 3 and the 6, check. If I pick the 2 and the 8, the 1 and the 4, the 2 and the 4, any of these 2, yes. So by the pigeonhole principle, I've succeeded. But now think about it a little more broadly. What could we generalize? A lot of times you're not going to be given a problem that's this concrete and this specific. You're going to be given a problem that's going to say, okay, suppose here, instead of picking any 6 numbers, suppose I told you to pick any, I don't know, let's say n plus 1 numbers. And maybe I'll make it m so it doesn't conflict with our notation. M plus 1 numbers. And the numbers go from, instead of 1 to 10, they go from 1 to 2m. Then, is it still true? Is the conclusion still true? There are 2 numbers such that one divides the other. Well, here, the number of balls is no longer 6. 6 is 5 plus 1, right? So this is going to be m plus 1. And how many boxes do I want to have? Well, now my number of boxes is just going to be m. And does the same strategy work? That's what we really want to ask ourselves. In practice, you're going to be given a problem like this with m. In reality, if you can do it for m some reasonable number like 5, then you can do it in general. So keeping it concrete like this and making it specific will help you see the general answer. So we have this pattern laid out for us. And we have this solution laid out for us. So let's solve this one in complete generality now. So what's our solution? Well, again, I'm going to make my boxes. So what are my boxes going to be based on? I'm going to pick, we saw it worked really well when I picked odd numbers. So I'm going to pick 1, 3, 5, 7, 9, all the way down to, let's see, 2m is my biggest number, so 2m minus 1. This gives me a total of m boxes, 1 for every odd number, so I have half of 2m, which is m boxes. Now, in the box with 1, I'm also going to put 2 times 2, 2 times 2 times 2. I'm going to keep multiplying by 2 and just keep going. And these are all the numbers of the form 2 to the k. K is already taken. 2 to the I. Okay? And then 3, remember we put the 6 with the 3 because that's 2 times 3. So this can get 2 times 3, 4 times 3, 8 times 3, and in general, it's 2 to the I times 3, right? So any number that's going to be like that. Okay, what about for 5? Well, 5, we put 10 with it. Okay, so let's put 2 times 5, 4 times 5, 8 times 5, and in general, we take 2 to the I times 5. And we keep going. This is going to have all the things of the form 2 to the I times 7. This will have all the things of the form 2 to the I times 9. And this will have, well, just itself. Now, we want to make sure that every single number appears here. It happened for 10, but let's just think, does that really happen in general? Are we still going to have that property? Well, every number is 2 to the something times an odd number. That odd number might be 1 if your number's even, for example. Sorry, not if your number's even, if your number's a power of 2. But every number has a bunch of 2's that we can pull out and something left over, okay? And that something left over can be any odd number. So every number fits inside of one of these boxes. So every single number is going to appear on my list. And how many boxes do I have? Well, I still have just m boxes. So by the pigeonhole principle, if I choose m plus 1 numbers, then I have to choose 2 from the same list. And those 2, because the way I've described them as increasing powers of 2 by multiplying them, every pair of numbers in the same row, one of them will divide the other. So we can solve this general problem. But to come up with this kind of solution, this sort of very abstract number theoretic solution, it really helps to make the problem as specific and concrete as possible. So when you're faced with something like this, pick m to be something specific and not too big. 5 worked really well for us because numbers 1 to 10 were something I could write down. So when you're faced with a problem, if you recognize pigeonhole, that's fantastic. Now you've got information about your balls and boxes. If it's still hard to visualize what those boxes should be, make the problem more concrete. We'll do more examples in class, so I look forward to seeing you in lecture.